into this thing, or is it just a prime time California machine or just a U.S. continental machine? If it's a 24-hour service, then I would be concerned about what's going on during these non-prime events. But other than that, those are the cron events that I'm assuming are occurring in non-prime. So I'm just going to look down in the lower data here and see what I see. So a majority of my drives do have their millisecond range, except for the cron events staying under 20 milliseconds. And then associated with these cron events, there are things that are going up higher. So my service times were in the 20, and my wait times are in the 10 to 20. So ignoring the cron events, it's within tolerance. It's within what I would consider an acceptable range of wait times. Disk busy, those were all the time, prime and non-prime. So even though you see the cron events here, you can still see that it's way above that threshold all the time that I said was 20% busy. So I'm more interested in why these drives are busy rather than the service and the waits, ignoring the cron events. Okay? And that goes then back to what's the I/O request size like and what's the file system configuration like. I'm going to just keep going here. Write blocks, I can see a particular drive that has a lot of writes. It looks like S6D2 again. That was the one that we saw before that had the high busies. And then we also have S0D4. One other drive in here, but since that only occurred one day in the month, I'm not going to pay attention to that one. And most of those writes were, or most of those blocks were writes. So this is reads and writes added together. And then there's just the writes. There's the total number of I/O operations. And again, there will be a correlation between I/O operations and busies. Because if I'm doing lots of little I/Os, then I'm going to be a lot more busy. So my read and write requests, I typically have queue lengths anywhere from 20 to 80. But again, these are cron events, and I'm going to ignore those, so that puts me in the range of 20 to 35 as a normal queue length for these two particular file systems. So everything I'm doing right now is just trying to get a baseline on a reference, and then when you look closer, you know whether you're in a normal interval or not. I'm going to get out of there. Okay, let's try a different machine. I wanted to look at two other machines, but during lunch I looked at EFS and there was nothing going on with it. It wasn't worth looking at. Too small to load. So I want to look at Clink, and everyone should be able to log into Clink. Use your normal Egan password. And then tilde DAW bin SPV. Now Clink is used as a file server, but it's also used to build. In fact, you can see some of these other file systems that are there. Linux building and a couple other directories that are used by some developers. I'm just seeing what some of their file system naming conventions are like. Of course, this we're going to find out is a big home directory. Still don't have that running. I think it's hung. Hang on a second. One of my mistakes was I'd run it before as root, and it didn't have permission to remove it as root. Oops. Okay, it worked. So let me try it again. So I'm going to skip the inventory for the moment. It's like do. It's a 16 CPU system with about more memory. I think 4 gig of memory or something. So like I said, every machine is different. Again, this machine, CPU utilization is not very high. It'd be hard for me to sell them more CPUs. I'm getting up to about 20% utilization across, I've got the 11th to the 19th, so I've got about 8 days worth of data on this particular system. Riding on top of everything though, look at these I/O events where I've got processes waiting on I/O. Leave that alone. My system time is a lot bigger than we've been covering so far. And a server like this is going to have higher system time, but I'm getting up to 45% system time. I might on this machine want to set off an alarm mechanism to say at 15% track with PAR what's happening on the system. So the next time one of these storms comes along, I've got a PAR trace to tell me what's going on. And 15 seems to be pretty good for week 1, 2, 3, 4, 5, 6, 7, 8 different events within a week. Without PAR, I can't tell much more about that system time. I can't tell if it's reads or writes or you name it. If I were on Unicos, I could because we did track it. Wasted time, wait I/O is most of it, and idle. I'm just going to zoom down here to look at the interrupt and S break. And interrupt is only getting 1, maybe 2%, not bad. And no S break indicated during the past week. And now looking at my wait I/O, it is split between wait FS and wait swap. So that tells me I'm running out of memory, and I'm also running out of buffer cache buffers. So CPUs are not oversubscribed on this system, but memory appears to be, and I/O appears to be, at least the buffered cache I/O. So let me take a look at, before I go on, the queue lengths. So our CPU queue length was anywhere from 4 to 10 processes. This was a 16 CPU system. So when I divide the queue length by the number of CPUs, I'm getting less than 1. At the most, I'm getting half of the machine committed. So all those secondary cache thrash stories and barrier synchronization problems are not on this machine because of the type of workload that it's running.
What's this machine doing?
It's an NFS server and also doing kernel builds. And you're looking at BuffView, aren't you?
Yeah. What?
Yep. Now let me get there. So I have anywhere between 2 and 8 or 2 to 10 processes on the run queue, and the I/O queue isn't too bad. It's only between 1 and 3 or 4. So there aren't a whole lot. So we're seeing wait FS a lot, but there aren't a whole lot of processes waiting on I/O. The question now would be, what were those processes that were waiting for I/O? And I can only get that from 2 different things. One would be accounting, and one would be the casing name D using PS at the time that you see it running. Now I have accounting turned on this machine, so I'm going to go under the command summary and take a look at what commands are doing all my I/O. Oops, guess not.
Oops.
We'll come back to that, see what happened. The next one I'm going to try is memory. So this is SAR little r. And this is my virtual memory reservations. I'm getting pretty low right here. This was the end of last month, but I still had 600,000 pages available. Swap left, I am allocating on swap. Now we're at the 19th right in here, so I can see that my swap left, I've actually got stuff coming off of swap and I'm freeing it up slowly. But still in the past week I've had several events where large processes come in and consumed my memory. And I bet those will match with the CPU utilization ones that we had. Actually, we would have had to break it out by swap. Let me just do that one again. So my point was that these reds are occurring when I'm swapping, and the blues are when I'm allocating on swap, so there ought to be a correlation. If I can get them right. This blue one here matches with what looks like the red there. I got 3 bumps here. Those are those 3 bumps. I've I've got one here, which is that one. I've got two tightly coupled that are there. So these are correlating. Here's one that matches this red one here. We've got two in here, there they are. So every time we started allocating on swap, we actually had processes waiting on pages from the swap device. Now on this machine, at this point, I'd be asking what's taking all my memory and is it important? And if it is, I could be looking at advising them to add more memory. If I can't make the program smaller, I may want to add more memory to the system. And physical memory left, we can see that memory is fairly well topped off, but we still have typically about 15,000 pages left on the system. So there's still lots of memory left on the system, but we still have paging going on. So I'm going to look at the memory utilization itself. So here's in percentage. My memory utilization is typically, I'm running pretty full, 95% memory utilization. So I'm using about 95% of my memory and topping it off pretty good. Now this is a bug again, not with SPV, but with what the kernel is exporting. SAR will show those numbers too. In fact, Nashville, or NASA in Huntsville, Alabama, got fooled by that wrap number and said we got plenty of memory free when in fact they were out of memory and were swapping. So here again is my memory used, or memory total versus memory used, and I'm topping off pretty good on the system. Now this is just showing my kernel size. So in this particular machine, the blue is my kernel, and on top of that is red, which is my FSCTL data, my metadata. And then on top of that, we can't see much, but the green is my dirty data. Now the green is getting laid right on top of the red, so it's pretty hard to see. So these are events. Well, we got a week here, and we got 1, 2, 3, 4, 5, 6, 7, 8. In fact, most recently, our kernel seems to be rather high. So Warren was probably looking at Buffview a few minutes ago. If he'd looked at a different time on a different day, he might have seen something different. So now I've got perspective, and right now the kernel appears to be about half my memory. And users, and on top of that then, by the way, that's metadata. That's inodes, directory name information. And then on top of that is my clean data. This is data that I have held busy for the last 5 seconds and I'm keeping it busy. If I let it go and don't use it for 5 seconds, it goes from clean to inactive. Now that 5 seconds is a rough number, it depends upon your overlay. For a while it was 100 seconds, then it went down to about 5 seconds, and in my last class it seemed to go back up to about 60 seconds. So when I get into pressuring buffer cache, we'll take a look to see how long it takes to go from clean to what's called inactive. So this is just showing the kernel, and my kernel is typically rather high in memory, and a majority of that here is my metadata or my inodes. And then the last one here was my total memory utilization, showing user space right on top of all that. By the way, that bug occurs when you run out of memory, when you get close to 0. So this is my total memory utilization. The blue is what the kernel is. The red is kernel plus the pieces of the cache. So again, my cache, including my kernel, is anywhere from 50 to 80% of my memory being used. And then user space is running right on top of that. So there are a couple of events here where I basically ran out of memory and then we started swapping. So except for this was probably the weekend, the 15th and the 16th, the rest of the week I'm quite busy. I'm going to look at disk. It's It's an IO-bound machine. If you are on Clink, pop up BuffView while we're talking about this. And when BuffView takes a while to come up, that's a good indication that buffer cache might be the contended resource. Not always true, I'm just being generic. There's BuffView. So on Clink, we've got 250,000 buffers, and that's why the kernel is growing so big in this machine. If we looked at do earlier in the week, we saw the kernel was very small. This morning I reset the NBuff, and Warren ran some I/O, so I expect to see the cache having grown on do with the code 1s and 3s that we're running. And out of those 250,000 buffers, 186 of them are my metadata, and right here, 68,000 of them are for the share file system, 55,000 for the I/O file system, 32,000 for the data file system, 15,000 for whatever is on S2D6, and then we've got 6,000 that is on /courses, and then lastly temp. So those would be the file systems where all my, well, that other one was a file, where all my buffers are being consumed. Okay. Other things in here, by the way, if it's a question mark, that just means we did not want to look up the file name. Maybe it's a long lookup and we didn't want to have to go through the whole process of getting the name. Also see people building some kernel debugs. Anyway. So looking at that system now, again, most of my service times, I'm going to ignore these two, but most of my service times are anywhere between 20, let's see what we get here. There are a few that are going above 20. There's one particular drive riding on top that looks rather busy, a couple of them actually. They're between 50 and 20, but it was this red one that painted on top here.
Line of coloring.
Yeah. And with this many drives, again, SPV is just going to give you an idea of what they all look like, and then you have to pull them out individually. That one looked like S3D3 because it was a dotted red pattern. This is where it'd be nice to have a three-dimensional view. And PCP can give three-dimensional views, but I don't have any tools that look at the whole data set at once. You have to slide things back and forth in the window. Again, if I go under SPV, I can look at a particular drive. Let me get rid of that one. The next one was my wait times. Now I did have a 2-minute wait on one particular drive there in the past week.
D3 again.
S1, D3, yeah.
S0, D3, or is it S1 or S0?
It looks to me like S1, D3. Again, once using the -A allowed me to be sure when I see it there, then I might look at it more closely here. So I'm in the process now of looking at the rest of the wait times, and we're still, right now, we're at 1 second. So right there is a 1 second wait, and I can see several drives that are showing up on me. So looking at this machine, I would still be looking at file system layouts. We've done everything that can be done to the buffer cache. It's growing as big as it can, and there are several other things that were done with the cache as well. So this machine really needs more disk drives, or at least getting the drives more actively involved, spreading out the I/O across the disk drives. And there are already quite a few drives on the system. Let me see what we've got for busies. And here now I see a whole bunch of drives that are also very busy. So I typically see them under 10%, but then there are several drives, looks like maybe 15 drives, that are kicking up there above, say, the 20% range. And some of them getting 95, 100%. And again, that red one looks like the same one, S3D3 was the one that I thought it might have been before. So let's take a look at S3D3.
You ever use DK staff?
Yeah. We've also got something called bdiskmon that's useful to watch things. I'm not sure how it works on the newer systems, but on do, in my bin directory, so I'm looking at S3D3. So this one is giving me my auto statistics, but what I was more interested in was bdskmon. Let me go to my bin directory. And that's a little, oops. Let me go to root. Try it again. I consider that a little bit more friendly.
Oh, yeah.
Okay, so it's curses driven. I'm seeing, again, this is in my toolkit, but it's not supported. A person that wrote it left SGI, Paul Helvig, who also wrote the vStore utility. So I do like this, but I don't know how it works on the newer drives, or whether it's dependent upon newer drives. vStore had to ping the drives to get information. I don't think this does. So this should be still workable. So we get the disk drive, the number request, the bytes transferred, reads, writes, and then overall activity to the drive. Okay. So that one I like a little bit better than DK stat. DK stat it's just not as friendly. But they're all getting the same counters. Okay, this is the same counters that SAR is getting, they're just formatted differently. Okay. So we're looking at S3D3. So my service times are fine, between 10 and 20 milliseconds. My wait times weren't too bad. Again, these cron events, those almost make me think swap. They almost look like the same way that the swap looked a little bit earlier. So I don't know what's on that particular drive, S3D3, but if swap's there, I'd be concerned. I'm going to ignore the blocks transferred, just get to busies. And there, this was not the drive I was seeing before, but busies are going above 20%. But it wasn't the drive I was looking for. Anyway. Let's see what's happened to do now. So I'm just trying to look at some different machine examples.
So the fact that they're running out of buffers on do, isn't they can't do anything because they're limited by memory now?
Yeah.
So the best thing they can do for do probably would be throw some memory in.
Well, remember my order, fix the applications first. So I want to make sure who's using the memory and whether it's politically correct and stuff. But in that scenario, you're right, there's nothing we can do about that. So the second thing would be to size the OS, which has already been done. We're using our memory to the maximum and we're making trade-offs between users and buffer cache. So the third thing then was to load the level the load off, which we can't do on a file server like that. So that's not an option either. So the next thing is to add more hardware. But I would still advise you to solve the file system issues before you solve the buffer cache issues.
It's just, I wonder why share is having so many in-buffs open.
That would be the number, is that system over on the left, that'd be the number of inodes that are in it.
So it's a really humongously big file system.
No, a lot of files in it.
Well, okay.
A lot of metadata. We don't know how big the files are, just a lot of metadata.
Okay.
Just like on Fido, the var spool news had a lot of the memory being used for the system metadata, but they were small files, not that we looked that far. But that's simply saying how much metadata am I describing. So if I've got all my users in one one file system with lots of files per user, it could be very high.
Actually, it's 101 gig file system.
You said, oh, that's the size of the file system. How much memory? You're on Clink still?
291 megs.
You're on Clink still?
Yeah. It's down to one empty buffer. It's been running 0 lately.
You said 0 on number of buffers?
Yeah.
Okay.
0 empty.
So he's looking at buff view. waited 10, 15 minutes before for Buffview too. And again, keep in mind that buffer cache may be contended for right now, but by the time Buffview is able to get the buffers, whatever was holding the buffers may have released them. So you may be looking after the fact. So I could be sitting there for 15 minutes waiting for a buffer. Well, some other application is taking all the buffers. It finishes, or it gives me an opportunity. I get my buffer, and now the application's event is done, which is why I got my buffer. So he was saying we got 250,000 buffers, 176 are from my metadata, and it was the share file system, 64,000 of those buffers describing my metadata. But what I was wondering was, how much memory is it? It's using basically a quarter of a gig of physical memory to hold that data. Okay.
It does have 380 megs of memory still free, so that's because of the min-max levels.
And min-free. There's another one in there, min-free. So it's a 4 gig system, and just that file system is taking a quarter of a gig to hold the metadata. So maybe I've just got too many things in one file system, like if it's a home directory, I might be splitting that into home 1, home 2, those sorts of concepts. But you're still going to have, if that's the number of data, whether you put it in one file system or spread them across file systems, you're still going to have the requirement of possibly needing those metadata inodes and stuff, like on a news server. Now he was also pointing out that empty is down. That doesn't mean that I'm out of buffers. I can still recover a buffer if there are buffers not busy anymore. So the real question is how busy are they? It's empty, but 5 seconds later it might get flushed. There we've got 4. It might get flushed or released and then available again. I can always get a buffer from data as long as it's not busy. I'm going to go to F and type in BSY. So what I'm trying to say is that you can have empty down to 0, and that's not such a problem. What I wish it had was another metric that said how many buffers were busy. So if I have 250,000 buffers, how many of them are actually being used and held within the last few seconds? And here, there's not a whole lot of busy activity at this particular time. So I am able to recover the buffers. So even though I'm empty, there's still buffers available for me because they're not being marked as busy. So when people pop up Buffview, I am concerned when I see empty, but what the other two stories are files toggling in the list, meaning that they're fighting thrashing. If you got things shifting in the list, that means you're thrashing in your file system buffer cache. And then if I go to the busy flag, how many of them are actually busy? And I'm not seeing a whole lot of busy right now, which means I should be able to get a buffer rather quickly. And if I do a VI, okay, I have reasonable response, even though I may have wait IO, all of it buffer cache. Of course, this isn't too bad. This is borderline. I said over 20% was where I started worrying. There was a 48% burst in there. 39, 29. But none of these tools tell you how many are actually busy. Now you can use Buffview on batch. There's a B option. So you can get the whole buffer pool. With interactive, you're just clipping and looking at the top. Okay. So I might want to run it and then specify a particular flag that I want, and I can also change the order, or I can say don't show metadata or don't show data. Again, with Buffview, there is a question mark option. There we are. So question mark, and these are all the different options I can do interactively, and these are the different flags that I can look at. So I can look at just dirty buffers that are written but have not flushed the disk yet. I can look at busy, that was the one I cared about. The swap doesn't work, or at least hasn't worked up till now. We don't see anything in there, but I always hoped that that would show me what pages are out on swap. But I've never seen that actually show me anything useful. Delayed allocation. You were asking about fragmentation. One of the things that IRIX does is delay the allocation as long as it can. The intent of this is to be able to get a better idea of how big the file is, and then I can allocate it. If I allocate it right away and it grows, then my allocation was bad. So what they try to do is, with delayed allocation, save that decision until more of the file is in buffer cache. And then I can make the allocation and flush it to disk, and that would avoid the fragmentation. Now the disadvantage, or let me put it this way, the things that are going to be good or things that are going to be bad with delayed allocation. Applications that are high I/O intensity. In other words, there's a lot of CPU I/O work. Code 3 was a high I/O intensity application. The high I/O intensity applications can punch the data into cache, and then the delayed allocation is to be quick enough to catch the difference and make a larger allocation. But for example, in the database market, I'm not high I/O intensity, and I'm trickling my I/O into cache, and then I don't get a very good idea. The cache is not getting the data quick enough. I don't get a very good idea of how big the file is going to be. So the applications that are low I/O intensity are the ones that are going to have a bigger fragmentation problem because of delayed allocation. And well, you can see we can look at inodes and other things in there. With OS view, to talk about delayed allocation on display 5, there is a file system buffer cache set of metrics called get block. And in there, here is my delayed allocation events. So right now, this particular system had 541 delayed reservations. How many are being freed, clean, how many are dirty, and how many are waiting. So this is an idea of what my delayed allocation schemes are doing. Now I wanted to go back to do for a minute. Oops. Because we changed nbuff on this machine. So let me just go through what we've got for data. On do, we've been oversubscribing everything on the system at one point or another. So there I see my CPU utilization. As we got more and more workload going, we can see that it's running rather high. Today we did have some I/O events going on. But in general, we've still been CPU bound. There was some stuff yesterday, or no, that's today still, this morning. And here's one that we were experiencing a few minutes ago, wait I/O time. Let's see, system time isn't very high on the system yet. I don't see any S-break or interrupt handler time. Oh, there was, looks like one there. A little bit of S-break wait time occurred there on the 17th on Tuesday. And the wait I/O time has been split. Mostly blue, which is on buffer cache, some res, which is on swap, and there was one green, which was direct I/O. I'm going to look at queue lengths. So look at this, my wait I/O queue for a while there got up to 45. That's where we were yesterday when I ran those workloads. Today my queue length is in the order of 10 to 15. But again, I've upped number of nbuffs, so nor did I recreate the actual workload that I fired off yesterday to get that queue length up there. And my run CPU ratio at one point was 300 or 30 divided by the number of CPUs. Also, I can see where one of my Go.Bottle experiments ran, where I scaled it from 1 to 2 to 3 to 4, and I went to a 3-to-1 subscription ratio, probably went up to like 32 copies of code 2 at a time. This was a go.bottle experiment that was visible in my data. So in general, my total run queue, remember we got up to 500 for a while yesterday? Ignoring that though, most of the rest of the time my queue length was under 60. And that again was exaggerated loads that I was trying to create. I'm going to look at memory, and this is the one that I'm seeing if we had any effect on. And yes, we can see it. So my memory utilization is all over the place depending upon whether we're here in running workloads or not. That's the same thing in pages instead of percent. But this is the one that I was looking for. So at the beginning of the week, I had dropped nbuff down to 400. And during the week, with all the workloads we were running, the kernel would grow a little bit, but as soon as we needed the space, it would get pushed back down. However, this morning, I upped nbuff, and now we actually got up to about 60% of my memory being used by my kernel and my cache. I'm just going to zoom into that area. And most of that is black, which is my clean data. So my metadata also went up, the green and the red. And then I've got my clean data. So at this point I got 85,000 pages that were going into buffer cache. And then when that workload was done, it released all that stuff and it got pushed back down, but to a different floor. It's not way down here like it was before. Now I'm going to try to actually create that experiment live and watch it with gross view. So here, for example, one thing we can see is the users didn't ask for memory, but I still dropped. However, in this case, the users asked for memory, and we've got a little bit of push down right here due to the demand from the workload. Same thing here. You're a little bit big. This one came along and it pushed it down. So we've got floors and we've got ceilings to this buffer cache. And what I've done with increasing nbuff is allow the kernel to grow to a high ceiling. But I still, at this point, could probably go even further. Because my cache is only going up to maybe 60% of my machine. Looks like I'm still able to use about 15% of my memory. And if this is a 2 gig machine, that's still quite a bit of memory. I'm just going to look at the file system. So this was number of calls, name I divided by I-get. There are times where I'm doing a lot of I-notes. And then this is the name I and I-get. So at times during these bursts, I'm getting as many as 1,000 calls per second to go off and get the I-notes resolved. And the red is saying the I-get, saying how many of those do I actually have to go to disk. So here was an event where we had to go to disk for a whole bunch of I-notes. We might have just created them as we fired off our workload. And I'm going to look at disk. Now again, it's where I need an inventory to know what my root and my temp and my home directories are, what disk drives they're on. Now even though I increased cache, I don't expect the disk drives to look much different between the rest of the week and today. Oops. Guess not. That was the problem I was experiencing earlier. So I'm just going to ignore that. So I think what we should do at this point is take a break. And then we need to come back and start talking about CPU.
How do you actually expand an OSPU?
Expand what?
Shift I.
Shift I?
Shift
Oh, in OSPU, yeah, capital I.
What kicks back though?
Capital D. I for insert, D for delete.
Oh, okay.
So you got to place your cursor over the bullet item and then do an I. But we need to get back to CPU and talk about CPU the rest of the day.
utilization's good.